Hello and welcome to helpyourmath.com. In this video, we're going to look at the natural base e. So we're talking about exponential functions, and we have a special one, and it's called the natural base. It's a base that's unlike others because you may notice that, well, it's a letter, whereas normally when we're talking about bases, we're talking about like 2 to the n or 2 to the x or a half to the x. And e is not that type of number. It's not a rational number, which is why it doesn't get to have a normal number looking thing. We use a letter instead. Whoever decided to use e, they decided this because it was named for the Swiss mathematician Leonhard Euler, who's credited for discovering this constant. So it's an irrational number, as I stated, and we can find the approximations for it in one of two ways. If we look at 1 plus 1 over n to the n, as n gets bigger and bigger and bigger, that's going to get us really close to this Euler constant. Or if we do 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus blah, 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 keep going to infinity, that would also get us this irrational number e. And in case you're not sure what a factorial is the product of a natural number and all the natural numbers that are smaller than it, with the exception of 0, because 0 is not a natural number. The natural numbers start at 1. And we would just say that 0 factorial is equal to 1. That's just by default, just so we don't end up with anything weird with the 0. So then, for example, 1 factorial would be just 1, because that's the only natural number smaller than 1. Or it's not even smaller, it is 1. And then 2 factorial would be 2 times 1. 3 factorial is 3 times 2 times 1. So again, it's just that number times every natural number smaller than it. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. And so if we just look at, we'll start with this definition. Let's start by plugging in 1,000 into our calculator. So if we plug for n, so 1 plus 1 over 1,000 raised to the power of n would give us 2.716923932, and that's going to keep going. If we plug in, let's say, 1,000,000 instead, let's see what the calculator gives us this time. This time I get 2.718280469, and then that's going to be repeating to something. And then if we want to see what the calculator says about e itself, you should be able to find an e key on your calculator. Mine happens to be not on the calculator. It's like above it. It's not a button. It's above a button. And by default, when you push that e button, it automatically is going to raise it to an exponent, because this is the natural base. This is its only purpose in life, is to be a natural base. So we're going to say e to the 1. And if we do e to the power of 1, I can't say equals because it's approximately, it's irrational. I get approximately 2.718281828, and this pattern, it's not a pattern, but the sequence will continue. As of now, I think they've calculated e to the 1,000,000th digit. Don't ask me how, don't ask me why, but this is all we need to know. So you can see as the value of n gets bigger, we're getting closer and closer and closer to the actual value for e. Oh, and then find the key on your calculator and see what e to the 1 gives you. So that's what we did just there. So this is the natural base. It's the natural base because it's a base that occurs in nature. So it's weird to us because it's irrational, but it occurs very frequently in nature. So it's our natural base. Okay, where do we see e? One place we see it is in finance. If we're looking at interest when it's compounding continuously, it's part of the formula interest equals principal times e to the rate times time. We see them in Bernoulli trials in probability theory. In statistics, we see it with standard normal distribution. In optimization problems in calculus, you might come across this. On this slide, we're just going to look at examples of plugging in values for exponents of our natural base e. So we're going to see f of 3/5. This would be e to the 3/5. So this is taking something and it's going to be smaller than 1, so this value should be smaller than 2.7, whatever e to the 1 is. And when we do this, we end up with approximately 1.822. It says round to 3 decimal places. There's a 1 in the 10,000th place. That would tell the thousandths place to just sit tight and stay where it is. If we look at b, we would have f of the square root of 7. That's e to the square root of 7. Square root of 7, that's in between 2 and 3. So it would be somewhere in between, like, 2 squared and 3 cubed. Let's see what we get there. So when we do that, we end up with 14.0940, 14, get that out there. Okay, 14.0940, that 0 would tell the 4 to sit tight. And these next two we're looking at when we have e to the negative x, or the reciprocal function, so that would be 1 over e to the x. F of 5 would be e to the negative of 5, which would be, so this is going to be something really small if we're plugging in negative 5. Oh yeah, we get 0.0067, so it would be 0.007. And then lastly, if we plug in f of negative 3.02 into that reciprocal, well, this time it would be negative of negative, which would end up being positive. So this is going to be e to the 3.02, really close to e cubed. And if we look at that value, we end up with 20.4912. That 2 would tell the 1 to stay the same. So just some examples of what we end up with when we plug in kind of random exponents for our natural base. On this slide, we're going to look at the graph of f of x equals e to the x. Since e is a number between 2 and 3, this is an exponential growth model, so the graph should look something like this, like any other exponential growth function. Because this is technically a parent function, we know that 0, 1 is a critical point on this, meaning to the left is where it's going to kind of be flatter, and to the right is where it's going to start going up bigger and bigger and bigger. So let's choose some values to plug in here for x and determine the value of f of x based on that. We want to choose points around the critical point, so I would suggest using just my standard negative 2, negative 1, 1, and 2. And then if we plug in negative 2 into this function, e to the negative 2 would end up being pretty small, 0.135. There's a 3 after that, so it would just stay like that. If we look at the reciprocal of e, we end up with 0.368 because it's 7, 8, and so the 8 would bump the 7 up. If we look at e, you might recall that it's 2.718 approximately, or so. And then lastly, if we look at e squared, this is just, a little bigger than 2 squared, we get 7.389. So we're going to do the best we can with this graph. Obviously, it's not going to be perfect. We are going to have a horizontal asymptote here at 0, so as the x values get smaller and smaller and smaller, it's going to get closer and closer to 0, which we can see because negative 2 is 0.135. That's really basically right on the y-axis, the x-axis. Negative 1 is going to be slightly raised up. Then we have 0, 1, 1, and 2.7. So we're going to maybe go right there. And then 2, 7.3 would be maybe here. Again, this won't be perfect. We want to use a smooth curve to connect these. So you can see that critical point, it gets flatter as we go towards the negatives, and then it kind of shoots way up as we go towards the positives. In our last slide,